Hello, this is Billy Younger again. We're here to solve a oscillation problem. This is called Oscillations Example 2, and it's specifically an application of the simple harmonic oscillator equation, where we're going to actually work out the initial conditions and everything. We're going to avoid actually plugging the stuff into the differential equation to verify exactly that omega is the square root of k over m, that sort of thing. But I'd highly encourage you to do that on your own. For this one, our only purpose is really just to show you how to apply the solutions that I just did in Oscillations Example 1. So let me go ahead and share my iPad screen. Problem says, consider a massive spring connected to a vertical wall adjacent to an ice skating rink. If the spring constant is 16.0 newtons per meter, the mass is 4.00 kilograms. The initial position is x of t equals 0 point zero seconds, is equal to 0.00 meters, and the initial velocity is v of t equals 0.0 seconds equals 2.00 meters per second. What is the complete solution of the resulting differential or the resulting SHO, our simple harmonic oscillator equation? So as always, we're going to start off with solution. So I use the word solution to begin the solving of the problem and to list the stuff we know and we need to know. So what I have here is K is equal to 16.0 newtons per meter. That is the typical units for the spring constant. We also have that the mass M is 4.00 kilograms. I've obviously made everything to 3 sig figs, so that helps quite a bit. We know that x0 is equal to 0.0 meters, but that x0 is also the same thing as x of 0.0 seconds. It's just easier to write it as x sub 0. And we also know that v sub 0 is equal to 2.00 meters per second. And that, of course, is v of zero point 0.0 seconds again. Now that we have all that, we also need to remind ourselves that the simple harmonic oscillator equation is any equation of the form x double dot plus some constant x is equal to 0. And in this case, we have Newton's second law of motion, summation of forces in the x direction, is equal to mass times d2x over dt squared, just gives us negative kx is equal to m x double dot, which means x double dot plus k over m times x is equal to 0. And our solution to that, at least the version that our textbook normally uses, is x of t is equal to a cosine omega t plus phi, where the angular frequency omega, which is also 2 pi times the frequency, which is also 2 pi over the period, is just equal to the square root of k over m, which for this quantity is 16.0 newtons per meter over 4.00 kilograms. And of course, that means omega is actually just equal to the square root of 4, and that turns out to be 2.00. And obviously, the units turn out to be radians per second. You might just call it reciprocal seconds or seconds to the negative 1 power. All of that is fine. Now we're going to use our initial conditions. What we know is x of 0 is equal to 0.00 meters. And we know that x of 0 from the solution is a times the cosine of the square root of k over m. Notice I went ahead and substituted what omega was, times t equals 0 plus phi. So that's what our initial condition and position gives us. And we can see from that 0.00 meters is equal to a times the cosine of phi, and that can only be true for phi equals plus or minus pi over 2 plus or minus 3 pi over 2, so on and so forth. So we know that that must be one of the phi's. I'm leaning towards taking the negative pi over 2, but we'll look at what the velocity initial condition gives us to decide that. Now we know v of 0 is equal to 2.00 meters per second, and it did say 2 as opposed to negative 2, so that means it's actually in the positive x direction. And this is equal to the derivative of x of t. The derivative of x of t is a, which is just going to be pulled out in front, times the derivative of cosine. Derivative of cosine is negative sine. And then we have to take the derivative of omega t plus phi, and the derivative of omega t plus phi is omega. So this is going to become negative omega a sine omega t plus phi. And remember, this is all evaluated at t equals 0. I just took the time to compute the derivative there. So now I've got 2.00 meters per second is equal to negative omega, we already know is 2.00 radians per second. A, we do not know yet. And then sine of 0 plus phi. So that's just going to be the sine of phi. With that in mind, we can now consider something along the lines of what could possibly phi be. Well, if we take phi equals pi over 2, then the sine of pi over 2 we know is equal to 1. If we took if we took phi to be negative pi over 2, then we know the sine of negative pi over 2 would be negative 1, and that would actually give us the negative we want. So we're going to adopt or take phi equal negative pi over 2. And once we have that, we can then say that 2.00, and we're including this fact as well, 2.00 meters per second is equal to negative 2.00 radians per second times A times negative 1, because the sine of negative pi over 2 is negative 1. So that negative 1 times the negative sign out in front gets the numerical values equal to one another, and that means A just needs to be in meters. So therefore, A equals 1.00 meters seems to work just fine. So we're going to take that, and we'll now say that x of t is equal to 1.00 meters times cosine of 2.00 radians per second times t minus pi over 2. And this is the actual solution of the differential equation and the solution for the problem. And you can check, of course, to make sure it matches the initial conditions, but that's really it. That's all you've got to do to solve any such differential equation that is a simple harmonic oscillator. Uh, I hope that helps. Have a good day. Bye-bye.